Welcome back to our journey through the annals of aviation, where we delve into the enigmatic and the extraordinary. Today, we're venturing into uncharted territory as we uncover the stories behind some of the most peculiar and fascinating aircraft ever to take to the skies. Built for the Air Force by Martin, the X-24A was a bulbous-shaped aircraft with 3 vertical fins at the rear for directional control. The X-24A boasted a weight of 6,270 pounds without propellants, with dimensions measuring just over 24 feet in length and nearly 14 feet in width. On April 17, 1969, Air Force Major Gerald Gentry piloted the X-24A for its inaugural unpowered glide flight. Gentry also commanded the vehicle during its first powered flight on March 19, 1970. Over the course of its operational lifespan, the X-24A undertook 28 flights, contributing to the validation of the concept that a wingless vehicle could execute unpowered landings akin to the HL-10 program. Decades later, in a cost-saving measure, the X-38 program managers opted to utilize the X-24A design, leveraging its complete aerodynamic database to minimize the need for additional wind tunnel tests that would have been necessary for a completely new design. The X-24A recorded its fastest speed of 1,036 miles per hour, Mach 1.6, with its highest altitude reaching 71,400 feet. Both of these milestones were achieved by NASA research pilot John Mank, who also piloted the craft on its final flight on June 4, 1971. The X-24B's design evolved from a family of potential re-entry shapes proposed by the Air Force Flight Dynamics Laboratory, each with higher lift-to-drag ratios. To reduce the construction costs of a research vehicle, the Air Force opted to return the X-24A to Martin for modifications. These alterations transformed its bulbous shape into a configuration resembling a flying flatiron, featuring a rounded top, flat bottom, and a double delta planform culminating in a pointed nose. John Mank took the helm for the maiden flight of the modified X-24B, piloting its first glide flight on August 1, 1973. He also commanded the vehicle during its inaugural powered mission on November 15, 1973. Notably, among the X-24B's final flights were 2 meticulously executed landings on the main concrete runway at Edwards, showcasing the operational feasibility of precise unpowered re-entry vehicle landings. These pivotal missions, executed by Mank and Air Force Major Mike Love, played a crucial role in shaping the flight procedures for modern space shuttle landings. The X-24B's last powered flight was on September 23, 1975, with Bill Danner at the controls, marking the conclusion of rocket-powered lifting body flights at the Flight Research Center. Interestingly, Danner also piloted the final X-15 rocket plane mission approximately 7 years prior. The X-24B achieved a top speed of 1,164 miles per hour, Mach 1.75, during a flight piloted by Love on October 25, 1974. Its highest altitude reached was 74,100 feet, accomplished by Mank on May 22, 1975. Today, the X-24B stands proudly on public display at the Air Force Museum located at Wright-Patterson Air Force Base in Ohio, serving as a tangible testament to its significant contributions to aerospace research and development. So many of the ingenious designs for aircraft put to paper throughout history never came into production or often died at the prototype stage. Some of these aircraft became conceptual legends, and others were instead renowned for their absurdity. The Bartini Beriev VVA-14 is a bit of both, not least because of its purpose and the colourful inventor behind its design. Perhaps the best means of understanding the genius behind the plane is to understand the genius behind its creator, Roberto Bartini. Bartini was born in the infamous city of Fiume, in what was then Italy and is currently modern-day Croatia. He would live through the early part of the 20th century through political uproar and the reorganization of states and borders that took place as a result of the First World War. He showed a passion for aviation early on in life, and more specifically for innovative aircraft designs and concepts, a passion which would lead the Italian engineer to the Soviet Union. After studying engineering at the ancient and world-renowned University of Bologna, often recognized as the Oxford of Italy, he joined the revolutionary aircraft manufacturer Caproni, where he worked alongside his mentor, the creative genius Giovanni Caproni. During his time at Caproni, Bartini was instrumental in making key innovations and design improvements in a number of the company's aircraft. However, Bartini's life would change completely when he was offered the opportunity to participate in aeronautical research in the Soviet Union. Fascinated by the career opportunities and prospects, Bartini accepted the offer. However, his decision to leave Italy was layered. Post-World War I Italy was politically and economically unstable. Furthermore, Bartini was an avid socialist and felt that the Soviet philosophy of strongly supporting scientific innovation would create potential for significant advancements in new aircraft technologies. From the moment Bartini arrived in the Soviet Union, he found himself directly involved in a variety of important projects. He began research at the Central Aero Hydrodynamic Institute, known by the acronym TSAGI, in Moscow, where he contributed greatly to a number of aircraft designs and concepts. However, Bartini had a knack for innovation and showed a notable prowess in engineering that made him stand out compared to his colleagues. He was quickly recognized for his notable mind when it came to aeronautics. His creativity and inventiveness earned him a reputation as a man with an unconventional but effective approach to aircraft design. Before he even began work on the Bartini Beriev, he designed the Bartini Stal 7, an elegantly designed twin-engine flying-wing transport aircraft, which would act as an inspiration for the Year 2 and the Year 4. Although the plane never went into production, it displayed the Italian engineer's uncanny ability to bring unconventional aircraft designs to life in a manner that similar engineers of his day were unable to do at the time. During the 1930s, Bartini began researching what would be the genesis of his masterpiece, the Bartini Beriev VVA-14 submarine hunter. Bartini began researching seaplanes and amphibious aircraft for their dual civilian and military applications. His early designs made use of retractable landing gear and hulls which were optimal for waterborne operations. Bartini's seaplane concepts were seen as impressive for their time and earned him significant status amongst his peers. World War II would see Bartini's expertise come to center stage. His contributions were essential to the Soviet Union's war effort. His experience was put to use on a myriad of projects, which included strategic bombers and reconnaissance aircraft. While Bartini's career was ultimately marked with success during his time in the Soviet Union, he did experience difficulties in his personal life. He underwent uncomfortable periods of political scrutiny and surveillance during the iron-fisted years of Stalin's regime. Yet Bartini managed to navigate the complex maze of Soviet politics and ultimately preserve his position as a respected aeronautical engineer. The apex of Bartini's career will be his work on the Bartini Beriev VVA-14 submarine hunter, a conceptual design which he began work on in the late 20th century. Even by today's standards, it was a marvel of engineering and design, capable of landing on any surface and taking off from any position. Known in Russia as the Vertikalno Vzletayashaya Amphibia or vertical takeoff amphibious aircraft, the VVA-14 was a highly experimental plane developed by the Soviet Union. It was intended to harness the abilities of a high-velocity aircraft combined with those of a seaplane. It also took advantage of the ground effect, compressing air in order to create a cushion between it and the water, meaning it could effectively function as a ship if needed. The question remains, why did Moscow want Bartini's airplane design to have so many different capabilities? The answer? Anti-submarine warfare, or ASW for short, and who better to design such a plane than one of the foremost amphibian aircraft experts in the world? The project began in the 1960s. Its scope was to create a submarine hunting aircraft that could operate in vastly different environments, from remote areas to coastal regions and large bodies of water. The VVA-14 had a uniquely long range and the ability to fly at unusually high speeds while carrying a large payload of radar equipment and other reconnaissance technology. The VVA-14's central fuselage extended forwards and backwards, housing the cockpit and engines. The wings were mounted above the fuselage with two pontoons directly beneath them. The pontoons not only allowed for water takeoffs and landings, but also provided extra fuel storage and contained regular landing gear as well. Perhaps the most impressive aspect of the plane, especially at the time it was conceived, was its VTOL functions. The VVA-14 used a special propulsion system to enable this. The plane came with two separate engine types, lift engines and cruising engines. The lift engines were located in the fuselage and could rotate to create vertical thrust for sustained hovering and VTOL capabilities. The engines responsible for lift were typically turbo engines, like the Kolesov RD-3635, and they were potentially capable of producing a titanic 8,800 pounds of thrust. Horizontal flying relied on turbofan cruise engines in the fuselage, like the Lyalka AL-7F. These engines produce a whopping 20,000 pounds of thrust. Different prototypes of the VVA-14 varied in the quantity of these engines used. Once finally in flight, the VVA-14's wings would rotate into position and the lift engines would reposition into a horizontal configuration. The cruise engines would then take over the forward flight function. The VVA-14's VTOL capability would have made it ideal for operating in extremely unconventional environments where other planes couldn't actively take off and land, such as bodies of water. This functionality also made the aircraft highly fuel efficient. The plane had channels which directed air beneath it, creating a cushion or gap which effectively allowed the VVA-14 to act as a hovercraft and therefore ship on the water. Overall, the plane's test runs were not unpromising. It reached an impressive top speed of 550 km an hour for a plane of its size, and water taxiing proved relatively successful. Perhaps most notably of all was the plane's odd design. Aside from being a truly hulking vehicle, it looked extremely modern for its time. The VVA-14 looked more like a comic book spaceship than a conventional airplane, with its back-mounted boosters and W-shaped body. This unique aesthetic was typical for Bartini's aircraft, which often sat at the cutting edge of aeronautical design. The conceptual outlines for the Beriev BE-1 and the Beriev BE-2500 reflected the very same ingenuity and prowess. Bartini's concept was undoubtedly a theoretically perfect answer to an increasingly hard-fought war against submarine technology. However, his prototype airplanes did not come through without their significant challenges and technical problems. One major issue was the plane's VTOL flight. The batteries needed to power the lift engines were never delivered, therefore the Kolesov RD-3635 was never used to help the plane take off or land vertically. The aircraft's highly complex design led to stability and control problems. Its unconventional configuration, using a variety of different engines, resulted in an inability to reach optimal stability. Furthermore, the plane's complexity meant maintenance was a nightmare. The engine's swiveling mechanisms added yet another layer of difficulty to properly maintaining and repairing the plane, all while raising the number of potential points of failure. And like any project, the VVA-14 suffered from budgeting issues. The cost of developing and testing the aircraft required multiple expensive prototypes, and Bartini's innovations, while genius, were extremely costly. Ultimately, the VVA-14 sucked up more resources than could be appropriately allocated to it. This is in part what led to the project's cancellation, especially given that the increased funding needed could not be justified against other Cold War expenses. In the end, priorities in the military were changing, and the Soviet Union and Navy decided to focus on an entirely different type of aircraft. The project was slowly deprioritized and cancelled. Bartini's submarine hunting beast never saw operational duty and ultimately fell to the wayside, ending up in a museum of aeronautics in Moscow, a shell and memory of the tireless work that went into creating an entirely new species of aircraft. However, despite the plane's ultimate failure as a project, Bartini's innovations and concepts were some of the most riveting and impressive for their time. He remains one of the earliest proponents of VTOL flight, and his designs are still unconventional and highly avant-garde by today's standards. Roberto Bartini knew how to push boundaries in a way that made him truly unique. His multidisciplinary approach incorporated disciplines from hydrodynamics to biomimicry. He turned to every source of inspiration he could in designing his planes. Perhaps that's why they were so futuristic. Maybe Bartini's VVA-14 went the way of all truly genius designs. Perhaps it was too far ahead of its time. Shining a light on his ideas means his legacy can go on, and that the genius that went into making his aircraft was not lost in vain. From 1963 to 1975, a fleet of lifting bodies operated at NASA's Flight Research Center, now Armstrong Flight Research Center in Edwards, California, showcased the capability of pilots to maneuver and safely land a wingless vehicle. These lifting bodies were specifically designed to validate the concept of returning a wingless vehicle from space and executing an aircraft-like landing at a predetermined site. These pioneering research vehicles, distinguished by their unconventional aerodynamic shapes, included the M2-F1, M2-F2, M2-F3, HL-10, X-24A, and the X-24B. The data gathered from the lifting body program significantly contributed to the knowledge base that ultimately facilitated the development of the Space Shuttle program. Unlike conventional aircraft that rely on wings for aerodynamic lift, these lifting bodies derive lift from their unique shapes. Fins and control surfaces were added to enable pilots to stabilize and maneuver the vehicles, effectively controlling their flight paths. With the exception of the M2-F1, all of these vehicles were powered by the XLR-11 rocket engine, the same type used in the Bell X-1, which famously achieved supersonic flight, breaking the sound barrier for the first time. The M2-F1, serving as a lightweight prototype, was unpowered. The original idea of lifting bodies was conceived around 1957 by Dr. Alfred J. Eggers Jr., then the Assistant Director for Research and Development Analysis and Planning at the Ames Aeronautical Laboratory, now NASA's Ames Research Center in California's Silicon Valley. H. Julian Allen, an engineer at Ames Research Center, concluded that a blunt nose cone shape was optimal for surviving the intense aerodynamic heating encountered during re-entry from space. The collective research efforts of Eggers, Allen, and their team culminated in the design of the M2, a modified half-cone shape characterized by a rounded bottom and a flat top, featuring a blunt, rounded nose and twin tail fins. This innovative configuration, along with subsequent lifting bodies, enabled them to be maneuvered both laterally and longitudinally, facilitating landings on runways rather than relying on ocean splashdowns typical of contemporary ballistic capsules used in programs like Mercury, Gemini, and Apollo. In 1962, Flight Research Center Director Paul Bickle greenlit a program aimed at constructing a lightweight, unpowered lifting body to serve as a prototype for testing the wingless concept. Resembling a flying bathtub, this prototype was designated the M2-F1. Crafted by sailplane designer Gus Briegleb, the M2-F1 featured a plywood shell enveloping a tubular steel frame meticulously assembled at the center. Construction reached completion in 1963. The initial flight trials involved towing the M2-F1 aloft using a souped-up Pontiac convertible, reaching speeds of up to 120 miles per hour across Rogers Dry Lake. These early tests yielded sufficient flight data about the M2-F1, paving the way for subsequent flights behind a NASA R-4D towplane at higher altitudes. The R-4D, a Navy designation for the C-47 or civilian DC-3 aircraft, towed the craft to an altitude of 12,000 feet, where it was then released to soar freely back to Rogers Dry Lake, marking a significant milestone in the experimental journey of the M2-F1 lifting body. NASA research pilot Milt Thompson flew the M2-F1 during the first series of tests. During typical glide flights with the M2-F1, the aircraft would remain airborne for several minutes, cruising at speeds ranging from 110 to 120 miles per hour. Remarkably, the M2-F1 underwent over 400 ground tows and 77 aircraft tow flights before being retired from active service. Today, this significant historical artifact is under the ownership of the Smithsonian's National Air and Space Museum. Currently, it's on a long-term loan to NASA Armstrong, where it has undergone meticulous restoration to resemble its flight-worthy condition, allowing future generations to appreciate its pioneering contributions to aerospace research and development. The success achieved through the M2-F1 program spurred NASA to embark on the development and construction of two heavyweight lifting bodies, drawing from studies conducted at NASA's Ames and Langley research centers. These lifting bodies were the M2-F2 and the HL-10, both of which were manufactured by Northrop Corporation. In the nomenclature, the M denotes manned, while the F signifies flight. The HL designation originates from horizontal landing, with the number 10 indicating the 10th lifting body design explored by Langley. Subsequently, the US Air Force also expressed interest in lifting body research, leading to the creation of a third design concept known as the X-24A, fabricated by the Martin Company. This model underwent modifications to become the X-24B, with both configurations actively participating in the joint NASA Air Force lifting body program at the Flight Research Center. The fundamental flight profile of these heavyweight lifting bodies involved air launching from NASA's modified NB-52B mothership at an altitude of approximately 45,000 feet, marking the commencement of their experimental flight missions. The XLR-11 rocket engine was then ignited and the vehicle accelerated to speeds of up to 1,100 miles per hour and to altitudes of 60,000 to 70,000 feet. After the rocket engine was shut down, the pilots began steep glides towards the Edwards runway. As the pilots initiated the final approach leg, they augmented their rate of descent to accelerate and harness momentum, executing a flare-out maneuver to decelerate their landing speed to approximately 200 miles per hour, mirroring the basic approach pattern and landing speed utilized by today's space shuttles. The inaugural flight of the M2-F2, which closely resembled the M2-F1, took place on July 12, 1966, with Milt Thompson once again at the controls. By this time, the same B-52 aircraft responsible for air launching the renowned X-15 rocket research craft had been adapted to also accommodate the lifting bodies. The M2-F2 was released from the B-52's wing pylon mount at an altitude of 45,000 feet during its maiden glide flight. The M2-F2, weighing in at 4,620 pounds without ballast, measured approximately 22 feet in length and boasted a width of about 10 feet. Tragically, on May 10, 1967, during the 16th glide flight, a landing mishap resulted in severe damage to the vehicle and inflicted serious injuries upon the NASA pilot Bruce Peterson. NASA pilots identified lateral control issues as a contributing factor to the crash of the M2-F2, despite the presence of a stability augmentation control system. Subsequently, when the M2-F2 underwent reconstruction and was rebranded as the M2-F3, enhancements were made to rectify these concerns. One notable modification included the addition of a third vertical fin, strategically positioned between the tip fins to enhance control characteristics. The maiden flight of the revamped M2-F3 occurred on June 2, 1970, with NASA pilot Bill Danner at the helm. This initial flight was a glide test aimed at assessing the performance changes resulting from the modifications. Notably, the modified vehicle demonstrated significantly improved lateral stability and control attributes compared to its predecessor, the M2-F2. Over the course of the subsequent 26 missions, the M2-F3 achieved remarkable milestones. It reached a top speed of 1,064 miles per hour, equivalent to Mach 1.6, with Danner piloting a high-speed mission on December 13, 1972. On December 20, 1972, during its final flight with NASA pilot John Mank in command, the M2-F3 attained its highest altitude of 71,500 feet before concluding its operational tenure. Today, the M2-F3 stands proudly on display at the National Air and Space Museum in Washington, serving as a testament to its pivotal role in aerospace history and its contributions to the advancement of flight technology. The HL-10, delivered to the Flight Research Center by Northrop in January 1966, took to the skies for its maiden flight approximately 11 months later, on December 22nd of the same year, piloted by Bruce Peterson prior to his injury in the M2-F2 accident. Over the course of its operational tenure, the HL-10 completed 37 flights, setting numerous program records along the way. Peter Hogue piloted the HL-10 to a remarkable speed of 1,228 miles per hour, equivalent to Mach 1.86, marking the fastest speed achieved by any of the lifting bodies. Just 9 days later, NASA's Bill Danner guided the HL-10 to an impressive altitude of 90,303 feet, establishing the highest altitude reached by any of the lifting body aircraft. Furthermore, on May 9, 1969, under the command of pilot John Mank, the HL-10 became the first lifting body to achieve supersonic flight. Featuring a longitudinally curved bottom and a laterally rounded top, the HL-10 sported a distinctive delta planform. In its final configuration, directional control was facilitated by 3 vertical fins, 2 of which were canted outward from the body, accompanied by a tall center fin. A flush canopy blended into the smooth, rounded nose. It was about 21 feet long, with a span of 13.6 feet. Its glide flight weight was 6,473 pounds, and its maximum gross weight was more than 10,000 pounds. The flights of the HL-10 played a significant role in shaping the design decisions for the space shuttles, particularly in the exclusion of air-breathing engines for powered landings. The HL-10 concluded its operational flights on July 17, 1970, marking the end of its remarkable journey. Today, this iconic craft stands proudly on public display at the entrance to NASA Armstrong Flight Research Center, serving as a tangible reminder of its invaluable contributions to aerospace research and development. Throughout the 1950s, major aircraft manufacturers in the United States were eagerly exploring the potential of vertical takeoff and landing (VTOL) technology across various military applications. With the looming threat of intercontinental ballistic missiles and thermonuclear weapons, the military sought VTOL aircraft capable of operating from small dispersed sites without relying on traditional air bases or aircraft carriers, targets that were increasingly vulnerable to attack. A key concept driving this pursuit was the notion that an aircraft with a thrust-to-weight ratio exceeding 1 could vertically launch, transition to horizontal flight for mission execution, and then return for a vertical landing. Such capabilities promised to eliminate the need for expensive and easily targeted runways, enhancing the aircraft's survivability and operational flexibility in a rapidly evolving strategic landscape. Among the pioneers in this endeavor was the Ryan Aircraft Corporation, which endeavored to translate this concept into a practical fighter aircraft for the Air Force with its X-13 Vertijet. However, like most other VTOL aircraft, the performance compromises made for their unique capabilities did not warrant its introduction in place of more capable conventional aircraft. The idea for the Vertijet originated just after World War II, when engineers for Ryan casually debated whether or not their FR-1 Fireball, which had a thrust-to-weight ratio of 1 at low fuel quantities, could take off vertically. The vertical takeoff idea soon advanced beyond the discussion stage. In 1947, the Navy's Bureau of Aeronautics enlisted Ryan for a contract aimed at exploring the technical complexities associated with developing a vertically launched jet fighter, a pivotal aspect of a broader initiative to assess the viability of submarine-based aircraft. Concurrently, the Navy funded a series of experimental tail-sitter aircraft comprising conventionally configured planes outfitted with large counter-rotating propellers designed to rest vertically on reinforced tail sections. Notable examples included the Convair XF-Y1 and Lockheed XF-V1, intended to utilize their high-thrust propellers for vertical takeoff from various naval vessels, thereby furnishing defensive air cover without the need for aircraft carriers. Ryan's engineering analyses demonstrated the feasibility of a comparable jet-powered design, augmented by a reaction control system capable of redirecting exhaust gases to facilitate control during hovering and low-speed flight. Subsequently, a Navy contract facilitated the construction of an unmanned flying prototype, which conducted its inaugural flight on October 20, 1950. This peculiar contraption, affectionately dubbed the Beast in the Backyard, was propelled by an Allison J-33 turbine and employed a ball-mounted nozzle to provide reaction control while hovering. Ryan engineers converted a B-47 fuel tank into a cockpit to allow test pilot Peter Girard to evaluate the testbed's suitability as a manned research aircraft, which sat on its tail to take off vertically. On November 24, 1953, Girard made the first manned hovering flight in a jet aircraft with this unusual machine. After Navy funding ran out, the Air Force became interested in Ryan's experiments and in July 1954 issued a contract to the company to construct 2 VTOL tail-sitter demonstrators designated as the X-13 Vertijet. This project, based on the earlier Navy design proposal, was to demonstrate the suitability of easily dispersible VTOL fighters. Under the guidance of Chief Engineer Curtis Bates, the X-13 emerged as a compact, single-engined delta-wing fighter, with its distinctive features being a set of winglets and fixed landing gear, elements that might appear ordinary to the casual observer. Spearheaded by Robert Furman and the Ryan Technical Section, the aircraft was meticulously designed to be transported on a specialized trailer, capable of tilting vertically to facilitate the launch and recovery of the X-13 during vertical takeoffs and landings. In late 1955, Ryan successfully completed the first Vertijet, serial number 541619, and on December 10th, Girard piloted its maiden flight. Initially equipped with a fixed tricycle landing gear, the X-13 underwent testing as a conventional aircraft. Furman and his team prioritized exploring the conventional handling characteristics before risking vertical flight testing. Following the resolution of oscillation issues through the installation of dampers, engineers affixed a temporary steel tube truss with clustering wheels to the rear of the X-13. This modification allowed the aircraft to assume a tail sitting position during vertical flight testing, eliminating the need for the complex launch and recovery procedures associated with the launch trailer. Pete Girard made the first vertical takeoff and landing on May 28, 1956. On the same day, the second X-13 made its first flight. The aircraft was agile and responsive in conventional flight. As the aircraft transitioned to a nose-high attitude to achieve a hover using the thrust from its own engine, a vectorable exhaust nozzle linked to the controls provided a straightforward and efficient means of control. To facilitate the delicate landing process, small bleed air thrusters positioned on the wingtips enabled minor adjustments to the pitch and yaw of the aircraft when necessary. Integrating both conventional and VTOL control systems, a stability augmentation system ensured smooth transitions without requiring abrupt changes to pilot control inputs. During vertical takeoff, the launch procedure involved raising the bed of the launch trailer vertically. This allowed the X-13 to hang from a cable suspended by 2 arms on the top of the trailer, featuring a partially retractable hook. For vertical operations, flat bumpers replaced each of the main wheels on the fixed landing gear, preventing damage to the fuselage underside if it swung into the trailer bed, thereby facilitating transportation. Subsequently, the pilot would increase throttle until the hook lifted off the launch cable, then maneuver away from the trailer and accelerate vertically, smoothly transitioning to conventional flight. However, vertical landings posed greater challenges and were perhaps the most impractical aspect of the Vertijet concept. Its primary drawback, akin to earlier tail-sitters, lay in the obstruction of the pilot's vision by the airframe, making it exceedingly difficult to accurately gauge the distance to the ground without external assistance. Although the pilot's seat pivoted 45 degrees towards vertical during landing, the pilot still had to approach the recovery trailer blind, with the underside of the fuselage facing the surface of the trailer. Constant radio communication with a ground observer was essential to talk the X-13 into position during the cumbersome process. A 6-meter, 20-foot long folding pole with marked gradations attached to the top of the recovery trailer gave the pilot a clear indication of the distance remaining before he contacted the trailer. Once in position, the pilot gradually reduced the throttle until the nose hook caught the recovery cable. On May 28, 1956, the X-13 executed its inaugural vertical hovering flight, initiating a series of summer tests where Girard and fellow test pilot Lou Everett practiced cable catching techniques using a 1-inch thick rope strung between 2 towers. To safeguard against potential damage during docking maneuvers with the trailer, Ryan engineers equipped the X-13 with a replaceable wooden nose. On November the 28th, Girard accomplished the first ever transition from horizontal to vertical flight and vice versa in the X-13. Then, on April the 11th, 1957, he launched from the trailer, seamlessly transitioning to conventional flight, and executed a vertical landing, successfully fulfilling the X-13's mission profile. Illustrating the concept of dispersed operating sites, the second X-13 captivated over 3,000 military officers and journalists with an impressive display at the Pentagon on July the 30th, 1957. However, competing programs diverted funds away from the project, leading to the X-13's final flight on September the 30th, 1957. Despite later programs like the XV-6 Kestrel and the AV-8 Harrier achieving operational success, the X-13 provided an effective solution to the challenges of developing a VTOL fighter within the technological constraints of its era. The Vertijet successfully completed all designated tasks and undoubtedly excelled as an experimental demonstration aircraft, despite the inherent impracticality of the operational concept. Ironically, by the close of the 20th century, the thrust vectoring system, originally pioneered on the X-13, would evolve into an indispensable component of advanced combat aircraft. In 1960, Ryan generously donated the first X-13 along with its launch trailer to the Smithsonian Institution. Gliding and soaring saw a surge in popularity across the United States from the early 1930s through the post-war era. Yet the challenges associated with getting a glider airborne deterred many potential enthusiasts. Glider pilots were presented with various options, all of which were relatively cumbersome and occasionally perilous, often requiring additional pilots, drivers, or ground crew. Among these methods, the most convenient involved taking off in tow behind either an automobile or a powered aircraft. In Germany, where gliding and soaring gained momentum shortly after World War I, groups of able-bodied individuals would sprint down hills, towing the motorless aircraft into the air using elastic bungee cords. While bungee launchers enjoyed considerable popularity in Europe, their adoption in North America was hindered by the wider availability of auto and airplane tows, alongside the region's hot and humid climate, which made this labour-intensive alternative less appealing. Powered winches were also utilised to tow gliders aloft, but this method posed risks and required a certain level of pilot proficiency. Additionally, it relied on a skilled winch operator. Once airborne, a pilot might opt to venture beyond the confines of the airport and embark on a cross-country journey, often culminating in a landing in a meadow or a field. Returning the glider to its home base necessitated significant group effort. The ground crew disassembled the glider into manageable sections, loaded them onto a specialized trailer, and transported them back by road. Glider enthusiasts found themselves dedicating more time to pre-flight preparations than actual flying, setting them apart from other aviation groups. Meanwhile, in the United States, William H. Bolus and Ted Nelson pioneered one of the earliest self-launching motor gliders. Bolus had already established himself as a proficient craftsman in glider design, with his BA-100 Baby Albatross and Senior Albatross models during the 1930s. Nelson, too, had developed several designs during this era. In 1945, they co-founded the Nelson Aircraft Corporation to manufacture a two-seat motor glider based on the popular Bolus BA-100 Baby Albatross. Dubbed the Bumblebee by the designers, it was officially marketed as the Dragonfly. While retaining the basic design of the Baby Albatross, Bolus and Nelson made significant modifications, such as widening the cockpit to accommodate side-by-side seating and adding individual flight controls for each occupant. They also incorporated improvements like tricycle landing gear with a steerable nose landing gear, additional vertical fins mounted on the horizontal stabilizer ends, and a hinged canopy. A pull-start handle for the engine was installed inside the cockpit. The aft section of the fuselage pod provided an ideal location for installing a pusher engine and propeller. Initially, Bolus and Nelson opted for a Reiter 4-cylinder two-cycle engine known as the 4034, However, this engine only produced approximately 16 horsepower. This wasn't enough power for flight, so Nelson decided to build a suitable engine from scratch. His new motor boasted 25 horsepower, just enough for takeoff and a gradual ascent. Due to the limited horsepower, the engines could only drive small, lightweight propellers. However, this was deemed acceptable as larger propellers added weight and increased drag. A drawback of the smaller propellers was the necessity for them to rotate at very high revolutions per minute (RPM) to generate adequate thrust. For instance, Nelson's engine required 3,900 RPM to lift the Dragonfly off the ground. Unfortunately, this high-speed rotation made the smaller diameter propellers considerably less efficient compared to larger propellers turning at lower RPM. This power plant and propeller combination enabled the Dragonfly to climb at a rate of 235 feet per minute at sea level. However, the additional weight of the engine and the drag from the widened fuselage resulted in a mediocre lift-to-drag ratio for the Dragonfly. The self-launch capability came at the expense of performance, which deterred many prospective motor glider owners, leading to only 7 Dragonflies being sold by Bolus and Nelson. In 1949, Nelson made another attempt at designing a self-launching glider, this time collaborating with Harry Pearl, with assistance from Don Mitchell. In 1973, Charles R. Rhodes generously donated his Dragonfly to the National Air and Space Museum. In the late 1990s, preservation specialists at the Paul E. Garber facility made a surprising discovery regarding the airplane. They found that the individuals who flew this aircraft had altered the induction system on the Nelson engine, creating at least 3 distinct configurations. Additionally, they observed that the engine mounted on the motor glider was incomplete, lacking several essential electrical system parts. This led them to suspect that either the engine or parts of it had been exchanged for non-airworthy components before the donation. The B aircraft Honeybee was a single-seat, all-metal light aircraft crafted by William Channer and Kenneth Coward, engineers associated with Convair, formerly Consolidated Vultee, situated in San Diego, California, USA during the 1970s. Its inaugural flight took place on the 12th of July, 1952. Remarkably, this aircraft has endured the test of time and now stands proudly on display at the San Diego Air and Space Museum, having been generously donated by the American Experimental Aircraft Association. The founders of B-Craft Associated Incorporated were instrumental in the creation of several innovative designs. Amongst these was the Wee Bee, a monoplane touted as large enough to carry a man, yet compact enough to be lifted by one. Demonstrated both in the United States and England, it secured a place in the Guinness Book of World Records as the world's lightest aircraft. Featuring a 2-cylinder engine and a tricycle undercarriage, the pilots assumed a prone position atop the fuselage. Following the success of the Wee Bee, the Honeybee emerged, with the inaugural model completed in 1952. This single-seater boasted an enclosed cabin, a high cantilever monoplane wing, and a distinctive V-tail. The designers then ventured into crafting the Queen Bee, a 4-seater marvel, which was finalized in 1960, further cementing their legacy of innovation in aviation design. Eventually, the Wee Bee and the Queen Bee were retired to the San Diego Aerospace Museum, but these 2 prototypes were destroyed by a fire at the museum premises on the 22nd of February 1978. The aircraft's structure featured simplified normal aircraft sheet metal, with a cantilever wing composed of flanged aluminum alloy ribs riveted to the main spar, covered by light-gauge aluminum skin. Its distinctive V or butterfly tail mirrored this construction, with control surfaces crafted from pressed fluted skins. The fuselage adopted a semi-monocoque structure, utilizing flanged aluminum frames and stringers, complemented by metal skin. Equipped with a tricycle undercarriage, the Honeybee featured a steerable nose leg and spring steel main legs. Typically, it was outfitted with a 48 kilowatt, 65 horsepower Continental engine, although various engine options were available. Notably, the Honeybee earned the distinction of being the first all-metal light aircraft design sanctioned by the Australian Department of Civil Aviation for construction by amateur builders. At least one such example was constructed in Australia. The earliest known instance of construction within the region occurred when students embarked on Project Honeybee at the Royal Melbourne Institute of Technology, VIC. Additionally, another Honeybee was in progress during the mid-1970s under the auspices of the Ultralight Association Victorian Division. It's documented that the construction of a couple of other Honeybee aircraft was initiated. However, whether any of these projects were completed remains uncertain. If indeed completed, it's likely that they would have been operated under ultralight or RAA, Recreational Aviation Australia, regulations. As of now, no photographs of these additional Honeybee aircraft have surfaced.
The X-15, designed to be purely and simply a research vehicle to provide aerodynamic, flight dynamic, and structural response data for use in the development of future manned hypersonic vehicles such as the Space Shuttle. No hypersonic wind tunnels, past or present, can provide accurate data for the design of a full-scale hypersonic airplane. The frontiers of flight today are the same as they were in the 1950s, the exploration of hypersonic flight. The X-15 will ultimately be viewed as the Wright Flyer of hypersonic airplanes. The X-15 flew to speeds and altitudes never previously achieved by winged vehicles. On the crisp, clear morning of November 9, 1961, a prospector working any of the many small mining claims in the bleak country around Mud Lake would have noticed a telltale broad white contrail signaling the approach of a strange formation of aircraft. If his eyesight was particularly acute, he might have discerned a giant Boeing NB-52B Stratofortress arrowing through Nevada's dark blue sky, flanked by two sleek little fighters, a North American F-100 Super Sabre and a Lockheed F-104 Starfighter. As he watched, he might have seen a long black dart drop from the B-52, followed by the sudden boom and crackling rumble of an igniting rocket engine. Boosted by 60,000 pounds of thrust, it leapt ahead of the big bomber and its chase planes, accelerating upwards as it burned a ton of anhydrous ammonia and liquid oxygen every 12 seconds. It arced into the trans-atmosphere, its white exhaust trail pointing like a finger toward the future. Not quite 90 seconds later, it was level at 102,000 feet, streaking towards Edwards Air Force Base in Southern California at Mach 6.04. Air Force test pilot Major Robert White had just become the first man to take an airplane to Mach 6, 6 times the speed of sound, flying the second of 3 North American Aviation X-15 research airplanes. Slightly less than 8 minutes and 200 miles later, trailed by another F-104 chase plane, the X-15, its propellants exhausted and now the world's fastest glider, dropped into a steep curve to a landing flare and touchdown on runway 18. Marked out on the hard-baked clay of Rogers Dry Lake, the world's largest natural landing site. The X-15 program was a natural outgrowth of progression of aviation since the time of the Wrights. The biplane had given way to the streamlined monoplane, and by the late 1930s, the first experimental jet engines had appeared, promising an era of high-speed flight. But as an airplane flew closer to the speed of sound, it encountered compressibility, the bunching up of air around it as it neared Mach 1, causing high drag, buffeting, changes in structural loads, and even loss of control and in-flight breakups. For more than a decade, until Chuck Yeager flew the first Bell XS-1, later X-1, to Mach 1.06 in October of 1947, it seemed that the speed of sound might indeed be a barrier to the future flight. Afterward, aviation accelerated rapidly into the supersonic era. Mach 2 fell to Scott Crossfield and the second Douglas D-558-2 skyrocket in November 1953, and Mach 3 to Captain Milburn Apt and the first Bell X-2 in September 1956, though tragically, he perished when the plane went out of control during its return to Edwards. By the time of Apt's death, the X-15 program was well underway. Its designers faced formidable challenges. Bell had built advanced variants of the X-1 that could excel at Mach 2 and 90,000 feet, and the swept-wing X-2 could climb above 125,000 feet. Both hinted at control challenges the X-15 would face. In 1956, when test pilot Captain Ivan C. Kinch coasted to above 126,000 feet, his X-2 was like an artillery shell following a ballistic parabola. Near the top of its climb, as the plane decelerated after its rocket engine ran out of propellant, its ailerons, elevators, and rudder were useless due to the very low dynamic pressure encountered as it passed through the upper atmosphere. The X-2 began a slow left roll, arced over the top of its ballistic parabola, and, as its speed and, consequently, dynamic pressure increased in the lower atmosphere, its flight controls regained their effectiveness, and Kinchlow was able to guide it back to a safe landing on Edwards Broad Lake bed. Clearly, flying above 100,000 feet, future rocket planes would require reaction controls, small jet thrusters such as those employed on the first manned spacecraft, in addition to conventional aerodynamic control surfaces. Aerodynamic heating and the high-altitude environment pose their own problems. Unlike supersonic flight, which is differentiated by the speed of sound and the distinctive crack of a sonic boom, hypersonic flight is characterized primarily by increasing aerodynamic heating with intensity hot airflows and sharply angled shock waves washing over the structure, their interactions producing even greater heat. The structure could not be conventional, for the plane would be subject to skin temperatures above 1,000 degrees Fahrenheit, necessitating extensive thermal protection. Inside the fully pressurized cockpit, the pilot would be more astronaut than airman, wearing a pressure suit and helmet capable of functioning in space-like conditions should cabin pressure be lost. Interest in hypersonic flight predated the supersonic revolution. The three great prophets of the space age, Russia's Konstantin Tsiolkovsky, the Romanian-German Hermann Oberth, and America's Robert Goddard, all advocated hypersonic airplanes as a means of flying into space, and German rocket enthusiast Max Valier, before his death and the explosion of an experimental rocket engine, recommended developing rocket-powered either planes as intercontinental airliners. In the 1930s, Austrian engineer Eugen Sanger and the mathematician Irene Brett undertook the world's first science-based hypersonic design, their so-called Silbervogel, Silver Bird. Proposed as a space transport and later as a global strike aircraft, it became an extraordinarily influential design study. Right after World War II, Joseph Stalin, according to a Soviet military defector, even sent a team into Western Europe on a fruitless mission to kidnap authors, hoping that Soviet Sanga planes would make it easier for us to talk to the gentleman shopkeeper Harry Truman. The combination of the Sanga-Brett study and example of the Nazi A4V2 ballistic missile greatly simulated post-war American, Soviet, and European interest in rockets, missiles, and hypersonic aircraft. While the Sanga-Brett study had been purely theoretical, the A4 program had extensively studied Mach 4 plus wing derivatives, one of which, the A4B, flew before war's end, though it broke up during its terminal glide to Earth. The Soviet-American race to develop atomic-armed ballistic missiles fostered heating and re-entry studies, evolution of the blunt body re-entry shape, and high-temperature materials research. It also encouraged studies of rocket-boosted winged global-ranging hypersonic vehicles, even orbital spacecraft. In America, from all this sprang the X-15 and X-20 programs, though the latter never flew. The roots of the X-15 reflected a broad base of military, industrial, and governmental research support. In 1951, Robert Woods, Bell Aircraft Corporation's chief engineer and a member of the National Advisory Committee for Aeronautics, prestigious aeronautics committee, called for development of new research airplane with performance similar to the A4s. His continued pressure led NACA's executive committee to endorse, a year later, investigating flight conditions between Mach 4 and Mach 10. The agency formed a hypersonic study committee under Langley Aeronautical Laboratory, now NASA Langley Research Center, engineer Clinton Brown, which subsequently advocated greatly expanded ground and flight research tests using models and specialized test techniques. The committee even suggested modifying the X-2 with a strap-on booster to increase performance above Mach 4, adding reaction controls for flight safety. Program delays and eventual loss of both airplane doomed that idea. In 1953, the Air Force's Scientific Advisory Board concluded the time is ripe for a Mach 5 to 7 hypersonic vehicle, and the U.S. Navy's Office of Naval Research issued a study contract to Douglas for a Mach 7 plus design, tentatively designated the D558-3. Air Force and Navy interest proved crucial to getting the X-15 program off the drawing board and into the air. The next year, 1954, marked the genesis of the X-15. Another NACA study team, headed by John Becker, undertook preliminary design of a Mach 6 rocket-boosted hypersonic research airplane. It had a nickel alloy and Connell structure, rocket-like four-fin tail, and off-shelf rockets from the Hermes program. Becker's study anticipated many of the X-15's features and encouraged NACA that summer to invite the military services to join with it in developing such an aircraft. In October, they formed the NACA Air Force Navy Research Aircraft Committee, subsequently known as the X-15 Committee. A joint program directive issued on December 23 gave technical oversight to NACA and design and construction authority to the Air Force. The Navy and Air Force would jointly fund the effort. The Air Force supervised the design competition in 1955 between Bell, Douglas, North American, and Republic. Bell's Robert Woods, who had launched the company's earlier X-1 effort, might reasonably have expected his firm to win, since it had already built and flown the X-1, X-2, and X-5. Douglas's Ed Heinemann, with his D-55-8 Skystreak and Skyrocket, plus the D-55-3 study, might have as well. Both companies produced relatively cheap designs, each promising to deliver 3 airplanes for a total cost of $36 million. Harrison's Stormy Storms, a veteran of North American's many fighter programs, led the design team that drafted his firm's entry at an estimated $56 million, the most expensive proposal. But both Bell and Douglas's designs were considered too technically risky, and Republic's, which was technically insufficient and also more costly than the Bell and Douglas proposals, came in last. Accordingly, despite the huge cost disparity, the Air Force notified North American on September 30th that it had won the competition. On June 11, 1956, after final negotiations, North American received a $42.9 million contract, about $349 million today, for the 3 X-15s. 3 months later, Reaction Motors Incorporated was awarded with a $10.7 million contract for their engines. The X-15 program involved far more than simply designing a new airplane, however novel it might be. Its rocket engine, pilot protection system, environmental controls and flight control system, as well as its flight test range, posed complex challenges. The X-15's XLR-99 engine, more than 3 times as powerful as the X-2s and 8 times as powerful as the X-1s, proved particularly risky. Developed by New Jersey-based Reaction Motors, the XLR-99 was based on the earlier XLR-30, used in the Navy's Viking high-altitude rocket program. Any hopes that the Viking experience would help with its design proved illusory. Unlike the XLR-30, which burned diluted alcohol and liquid oxygen, the 57,000-pound thrust XLR-99 burned 1,445 gallons of more explosive anhydrous ammonia and 1,000 gallons of IOX. More significant, however, Tycol had to man-rate the engine, i.e., make it safe enough for operation in a piloted airplane, capable of repeated use, and both throttleable and restartable in flight. This was not easy to achieve, particularly as its high-speed turbopump, a potential source of disaster, fed the engine propellants at a rate of 167 pounds per second. Eventually, the XLR-99 became a reliable power plant with a rated operational life of about 1 hour, about 40 flights before requiring overhaul. Such reliability came at a price for a far longer than anticipated development period, compelling North American to complete the first 2 X-15s with older XLR-11 engines for their proving flights. The X-15 required a complex flight control system, a conventional fighter-like stick controlled an all-moving tail that furnished pitch and roll control, but was used only during approach and landing. During high G acceleration, climb, and re-entry, the pilot relied on a side-stick controller, a reaction control system operating small hydrogen peroxide jet thrusters located in the nose and wings, furnished pitch, roll, and yaw inputs at high altitudes, where conventional controls were ineffective. Eventually, the third X-15s flew with an adaptive flight control system that automatically compensated for changing dynamic pressure, blending the reactor control system with the conventional aerodynamic controls. Since the X-15 was technically a boost glider, once it exhausted its propellants, the pilot had to carefully manage his energy to ensure he could reach Rogers Dry Lake. To help him in doing this, the X-15 would always be flown so that it had excess energy at burnout, which the pilot could use as bleed-off using large pedal-like speed brakes installed in the side of a massive dorsal and ventral fins. Unlike earlier rocket-powered aircraft that flew near Edwards AFB, the X-15 demanded a special flight test corridor, dubbed the High Range, running roughly 480 miles from Wendover, Utah, southwest to Edwards. Crossing multiple mountain ranges in the stark southwestern desert, the High Range was itself a notable technical accomplishment, foreshadowing the manned spacecraft tracking network NASA established for Project Mercury several years later. NASA furnished 2 tracking stations at Ely and Beatty, Nevada, as well as at Edwards. Furthermore, unlike research airplanes, the X-15 required a complex flight simulator to train pilots and undertake mission planning and rehearsal. The simulator was updated using data required during X-15 flights, with pilots typically spending 40 to 50 hours in it before undertaking the 10 to 12-minute flight. When the program commenced, it was hoped the X-15 might be flying by the end of 1957. Due to the complexity of its design and technical challenges involved, however, test flights did not begin until 1959. In the interim, NASA and the Air Force supported the X-15 development effort with extensive wind tunnel and free flight ballistic tunnel testing, evaluated reaction controls on ground simulator rigs and unmodified research airplanes including the Bell X-1B and F-104, and undertook extensive simulation studies to prepare for the crucial challenges faced by a hypersonic rocket plane having, for its first time, the lowest lift-to-drag ratio ever flown on a piloted aircraft. In October 1957, Sputnik had seized the public imagination, and the national debate over American science and technology that followed, NACA had given way to the space-focused NASA. Now the X-15 took on greater urgency and visibility as a symbol of America's progression into space. Vice President Richard Nixon presided over its rollout at North American's Los Angeles facility on October 15, 1958. A year after the Soviet satellite ushered in the new space age. It was a remarkable-looking aircraft, burnished metallic black, with thin wings and horizontal tail surfaces, and, because of the directional stability requirements of high supersonic and hypersonic flight, large meat-cleaver dorsal and ventral vertical fins, the lower half of the ventral surface jettisonable during landing approach so that the X-15's landing skids could be a reasonable size. Although planners had originally thought the X-15 would use a modified Convair B-36 as a mothership, the retirement of the B-36 and the availability of the more powerful and capable B-52A led to its substitution for Convair's giant intercontinental bomber. Early tests with the X-15 proved far from encouraging. Piloted by North American test pilot Scott Crossfield, who had been so dedicated to the project that, as it began, he left NACA for North American, the first X-15 AF-56-6670 made its maiden captive flight on March 10, 1959, followed by its first glide flight on June 8. During the landing approach, Crossfield encountered serious longitudinal control problems that pushed his piloting skills to the limit, necessitating adjustments to the boosted flight control system. The second X-15, AF-56-6671, made the type's first powered flight on September 17. Propelled by 2 XLR-11 engines, it reached Mach 2.11 at 52,341 feet. He completed another powered flight into Mach 2.15 a month later, but then, on November 5th, disaster struck when an engine fire forced an emergency landing on Rosamond Dry Lake, during which 6,671 broke its back. while the second X-15 returned to North America for repairs and installation of its XLR-99. Proving flights continued through 1960, with 6670 still equipped with its interim XLR-11s. The third X-15, AF-56-6672, was the first completed with the big tactical XLR-99. But during an Edwards ground test, the engine blew up, catapulting the rest of the airplane forward. Safe in its cockpit, Crossfield marveled at the X-15's strength and worried for the safety of crews trying to extricate him. The plane, like the second X-15, returned to North America for a rebuild. Not until November 15, 1960, 3 years late, would the X-15 fly with its XLR-99 engine, when Crossfield took 6671 to Mach 2.97, marking the end of its contractor flight test program. But now, the X-15 hits its stride. On March 7, 1961, Air Force Major Robert M. White became the first pilot to exceed Mach 4. He piloted the second X-15 across the hypersonic divide on June 23, attaining Mach 5.72. White completed a sonic trifecta by exceeding Mach 6 on November 9, as previously mentioned. Nor was the boyish airman the X-15's only record setter. On August 22, 1963, NASA research pilot Joseph Walker attained 354,200 feet in the third X-15, taking it into space. Marring this was a serious landing accident on November 9, 1962, that virtually destroyed the second X-15 and seriously injured NASA pilots Jack McKay. When an engine failure necessitated a heavyweight emergency landing on Mott Lake, 6671's skid landing gear collapsed. Even this setback was turned to advantage, for NASA lengthened the X-15 and added provisions for 2 huge drop takes and a dummy supersonic combustion ramjet engine installation on the shortened lower vertical fin. Eventually, on October 3, 1967, Major William J. Pete Knight reached Mach 6.7 flying this aircraft, designated the X-15A2. During the flight, unanticipated heating led to multiple structural failures, causing the scramjet module to separate from the aircraft and damaging the fuel jettison system. Knight, a superlative airman, landed safely. Sadly, shortly after Knight's remarkable flight, the fastest by a piloted airplane in the 20th century, Air Force test pilot Major Michael Adams, was killed in the third X-15. On November 15, 1967, during a high-altitude flight, it entered a Mach 5 plus spin, and it broke well above Mach 4 during an inverted dive into the lower atmosphere. The accident stemmed from a fatal combustion of instrumentation and control systems failures, plus human factors. Less than a year later, on October 24, 1968, the X-15 completed its last flight, its 199th, flown by NASA pilot William Dana. NASA attempted a 200th flight on December 20th, but Edward was typically swathed in snow. Planners took it as an omen and simply retired the craft. The first X-15 went to the National Air and Space Museum, where it may be seen in the Milestones of Flight gallery, and the second, the fastest airplane of the 20th century, to the National Museum of the U.S. Air Force. Altogether, 12 distinguished pilots, Scott Crossfield, Robert White, Forrest Peterston, Neil Armstrong, Joe Walker, Jack McKay, Milt Thompson, Robert Rushworth, Mike Adams, Bill Dana, Pete Knight, and Joe Engel, had flown the X-15 to speeds and altitudes never previously achieved by winged vehicles. Its research program consisted of an aerodynamic and structural heating investigation phase from 1959 through 1963, and a follow-on program utilizing the X-15 to carry experiments into the upper atmosphere or to hypersonic speeds. Much of the applications program benefited from the contemporaneous Apollo effort, but it also helped sensor and missile detection efforts. X-15 flights produced more than 700 technical reports, establishing a database still considered essential today, as hypersonics advances into the second century of flight. The X-15 was by no means a perfect research vehicle. Under some circumstances, it had dangerous flight characteristics, and heavy impact loads sorely tested its landing skids. During re-entry, In-flight reconnaissance effects could interact with its flight control system. Early on, researchers discovered gaps in panels that permitted the entry of hot hypersonic air into its structure, necessitating fixes. Cockpit outer window panels shattered from heat-distorted panel frame structural loads, forcing redesign, and its nose landing gear twice extended in flight due to thermal stress. There were several landing incidents and accidents, one major ground explosion, and, of course, the sad loss of the third X-15 with Mike Adams. But overall, as a product of the pre-computer design era and without the benefit of modern tools such as computational fluid dynamics and computer-aided design and manufacturing, the X-15 constituted a remarkable achievement and an astonishing productive research program bridging the age of flight and the age of space. Fittingly, two of its most distinguished pilots went on to greater fame in the U.S. space program. Neil Armstrong became the first man to walk on the moon, and Joe Engle became one of NASA's first space shuttle mission commanders. Today, Air Force and NASA researchers pursue Mach 6 hypersonic flight with the air-breathing Boeing Pratt & Whitney Rocketdyne X-51A Wave Rider scramjet research vehicle. Tellingly, its designation, X-51, was deliberately chosen and reserved to echo the X-15 and remind researchers of the remarkable aircraft that, a half a century ago, did so much to make hypersonic flight a reality.
This is our home in space, an island universe circled by the Milky Way. And within this glittering corral are more than 100,000 million stars. Yet this galaxy is only one of a limitless number. Each of the countless stars within our galaxy is a body like our sun. The sun that shines on us is far from the largest, yet it dwarfs the Earth on which we live. In spite of this seeming insignificance, the planet Earth has nurtured generations of men with imaginations that reach above and beyond the confines of this small spinning globe. To fly like a bird was long the desire of earthbound man. Many years before the Wright brothers made history at Kitty Hawk, men had searched for means to escape the heavy hold of gravity. Their successes were varied and limited, but they took the first steps on the stairway to the stars. But every flight, every new development in aeronautics added to the cumulative knowledge necessary to lead man to the threshold of space. It is now but a matter of measurable time before a new world opens to the adventurous explorers of outer space.
All muckluck hatches secured, Commander.
Thank you, Lieutenant. Zoom.
Zoom.
Checked bilateral conning pods.
Aye, aye, Commander.
This is Commander of the spaceship Star Skipper requesting blast-off clearance at 0100 and standing by. Prepare for blast-off, Lieutenant.
Aye, aye, Commander.
Hypersensitivitator intensity normal.
Normal.
Variation frenetic creeps at 2.06.
2.06. Check, Commander.
Atomocrylacine fuel supply normal.
Fuel supply normal, Commander.
Stand by for countdown.
Aye, aye, Commander.
Blast-off time minus 10, 9.
We've all seen space flight depicted in scenes similar to this.
7,
Well, it's colorful,
6,
but not quite scientifically accurate.
5,
I'm reporter Ed Fleming. I'm going to call on the help of our narrator, Michael Rye, and some outstanding space experts. We'd like to show you something of what is actually being done, and plans that are projected for future explorations of the moon and our neighboring planets. Every test, every rocket flight brings us closer to the conquest of space. one thing to launch a rocket into the sky, but it's something else again to envision a satellite in orbit or a space vehicle that might reach another planet, especially a manned vehicle. Right now, I'd like to get some opinions from a man who's one of the brightest names in the aviation history of our country, General James H. Doolittle, member of the National Aeronautics and Space Council and chairman of the Scientific Advisory Board to the Chief of Staff, United States Air Force. General, I know a lot of people are asking, why go to space at all?
I believe the conquest of space may unlock the door to physical discoveries of the greatest value to the human race. Our leadership in the world depends on being in the forefront of these exciting discoveries.
Another common question these days is, how soon will we have a man in space?
That depends on many factors. We must make rapid progress, but we're not going to take chances with human lives. After more is known about the problems now being worked on, we'll orbit the Earth with a manned satellite that can return safely to home base. And someday, man will finally escape from the Earth's gravitational field and will then truly be in space.
Do you feel the advantages of space control are primarily military or civilian?
I believe that there are bound to be major benefits in both fields. Right now, it seems that most military missions, even in the space age, can still be carried out most effectively by using the manned aircraft and the missiles that are currently in use and under development. However, this may not always be true, and we have to consider every possibility now and in the future.
Isn't that going to be expensive, both in money and in scientific effort?
Yes, but we must realize the conquest of space will probably be of greater importance than we can begin to realize at the present time. And if we do not expend the thought, the effort, the money required, then another, more progressive nation will. It is quite possible that an aggressor nation that dominates space will then dominate the world. We just can't let that happen.
Thank you, General Doolittle.
In approaching the problems of the conquest of space, energy is a prime consideration. Controlled energy exceeding anything man has ever known. Already the power plants in our modern missiles are producing horsepower measured in the millions. In the thunder-filled canyons of California, we are working night and day to concentrate that power. Other considerations are trouble-free guidance controls, protection against tremendous heat and pressure, and the unknown hazards of the hostile environment of space. The reliability of both man and machinery, for the slightest failure in space may be fatal. Of these, man is the greatest question. Machines can be designed and redesigned, but we have to take man as he is. Earthbound, man has evolved and developed in a protected environment. We are wrapped in a sheltering cover of atmosphere that filters out the ultraviolet rays of the sun and shields us against plunging meteorites. The higher man goes, the farther away he moves from his natural protective environment. As he climbs upward, he reaches a point where he needs an additional oxygen supply to keep breathing. Farther up, his blood would boil if he were not protected in some manner. And continuing to the lower edge of the stratosphere, he would encounter temperatures of 67 degrees below zero. We are investigating these conditions through such tests as the balloon flights of Air Force Colonel David G. Simons. Carried for 32 hours in an insulated capsule the size of a telephone booth, Colonel Simons rose to an altitude of 102,000 feet. At that distance, only about 1% of the Earth's atmosphere separated him from outer space. And in September 1956, Captain Ivan Kinchelow rode the Lightning of the X-2 up to 126,000 feet. However, these flights carried us only to the fringes of space. But little by little, we are opening the gates that lead to man's widest horizon.
Well, everything seems to point to the fact that with proper planning and preparation, man can live in space. But there's still a great deal of research to be done before this becomes a reality. Major General Dan Ogle, the Surgeon General of the Air Force, has many of his doctors and other medical scientists working in this field. General Ogle, what is the basic function of space medicine?
I would say that it is to discover how much man can adjust to the conditions of space and to help create an environment in which he can stay alive and work efficiently.
And how is that done?
By trying to simulate space conditions in our aeromedical laboratories and then testing man under these conditions. For example, we know now that his space cabin must be a miniature Earth with a livable atmospheric pressure plus insulation from deadly radiation, the intense heat of the sun, and the incredible cold of space itself.
What's going to be the toughest problem for space pilots?
Even after 10 years of Air Force space medicine research, there are probably some conditions out there we don't even know about yet. But we do know that one of our major considerations will be weightlessness.
What causes weightlessness?
It comes about when the space vehicle's velocity and flight path neutralizes the pull of Earth's gravity upon the ship and everything in it, including the man. That happens in outer space or in orbital flight. In space, of course, the condition can go on as long as the vehicle is out there, days, weeks, or even years.
You mentioned that weightlessness could be created in a certain flight pattern. Isn't that what's known as a ballistic trajectory?
Yes, let me demonstrate. The plane would fly a power dive first to gain speed, go into a curve, climbing like that, and it is at this point that the speed and curving of the plane exactly neutralizes the pull of gravity, and the pilot experiences a feeling of weightlessness. These are just a few of the problems we're working on, and from what we've already learned, we feel confident that man can adjust himself to conditions in space.
Well, General Ogle, I'm sure we're all looking forward to that day when we can put a man in space and bring him safely back again. Thank you, General.
However, before we can safely put a manned satellite into permanent orbit, there will be many experiments with unmanned craft carrying instruments. For one reason, such experiments are simpler and less expensive to project into space. The unmanned satellites will carry precise recording equipment to register the varying conditions they meet at different altitudes. These vehicles will probably be fairly simple to start with. As they grow in size, they will become more complex and more completely instrumented. With the aid of numerous scientific instruments, the unmanned satellites will give us vital information on radiation, meteorites, cosmic rays, and other aspects of the hostile environment which must be known more fully before man ventures into the dark frontiers of space. A satellite might serve as an eye in the sky for the purposes of military reconnaissance. In its flight around the Earth, it would keep a continuous watch on the land below for any indications of military buildup by potential aggressors, and by means of television, would relay its findings to a headquarter control station. And in this manner, it could also serve as civilian defense against freakish and destructive changes in weather conditions. A further step would be to launch a satellite to an orbit 22,000 miles above the equator. At this altitude, it would travel at the same speed as the rotation of the Earth, so that it would remain in a fixed position. This would be ideal for a wide-range radio and television transmitter. 3 stationary satellites might then become an international communications network that would be of tremendous value in war or peace.
But before we head for the moon, let's go through some of the steps that will get us there. The X-15 is a joint program of the Air Force, Navy, and the National Aeronautics and Space Administration. It's designed for flight at altitudes never before achieved by a manned aircraft.
The X-15 takes its shape from experience gained in the development of supersonic planes and missiles. But it has to be better than a missile, for it carries a human pilot, and it will have to make many flights. Suspended beneath the wing of a bomber, the X-15 is airborne for launching. Arcing up in a ballistic trajectory, it passes swiftly beyond the limits of previous manned flights. Like an arrow leaving the bow, it is in free flight after its propellant burns out. For a period of possibly 4 minutes along the upper curve of its arc, the pilot is in a condition of weightlessness. This offers an opportunity to study the effects of weightlessness on minds and bodies of pilots. At the top of the X-15 arc, conventional control surfaces are almost useless because of the small amount of air pressure on them. So, ingenious reaction controls have been built into the nose and wingtips to keep the ship in proper attitudes. These jets guide the plane by pushing it in opposite reaction to their force. As the plane descends in its curving flight, it plunges back into the heavier atmosphere, where its normal controls are again practical. But this heavier atmosphere develops the fierce temperatures of the thermal thicket, the heat barrier created out of speed and friction. Gradually, the pilot maneuvers out of the ballistic trajectory and circles down for a dead stick landing. As a means of getting a man into orbit, a Super X-15 has been proposed. The Super X-15 would be ground-launched, using a powerful liquid propellant rocket booster to supply the needed thrust. The booster provides the tremendous power necessary to release the grip of gravity on the plane. As the booster burns out, it drops away, and the engine of the craft takes over to supply the added thrust to place it into orbit. At the speed he'll be traveling, our man in space will cover the distance from Cape Canaveral to the South Pole in approximately 45 minutes. When the time comes for a landing at Edwards Air Force Base, the pilot will fire retro rockets to drop out of his orbiting course. Then he begins his glide to Earth. This will be accomplished in a series of dips in and out of the heavier atmosphere. This will be necessary for a gradual slowing down and to prevent the plane from burning like a meteor. The plane will actually glow like metal in a blacksmith's forge as it plunges into the blanket of heavier air. The successful orbital flight of the Super X-15 will be an important step toward the conquest of the moon and the nearer planets. Now let's return to Earth for a moment, and to our reporter to check on our progress in developing adequate power to accomplish this moving into and through space.
Hello again. I'd like you to meet Mr. George Sutton, President of the American Rocket Society and Hunziker Professor of Aeronautical Engineering at Massachusetts Institute of Technology. Mr. Sutton, how soon will we go to the moon?
Well, now, that is something no one really knows. But I suspect it might take 10 to 15 years. But first, we must develop manned satellites, and that is going to require a great deal of propulsive power. Here, you can see some of the largest test stands in the country. On these stands, we have tested the engines for Atlas, Thor, Jupiter, Redstone, Navajo, and other missiles. There is the signal for a test. Now, shall we watch it?
PG first on, PG first on. 15. 20. 25. 26. 27. 28. Camera sign. 30.
Wow, that's a lot of power. Say, how about the rocket that was used to launch the Army Explorer satellite?
That one was developed and tested right here. Of course, our first satellite weighed only over 20 pounds. But right now, we are working on engines that can deliver a thrust of 6 million pounds. And with these engines, we'll be able to put payloads of over 55 tons into orbit. Every step of the way must be thoroughly investigated before we take the giant step of sending men to the moon. Our first approaches to the moon are made with unmanned vehicles and chemical rockets. And lunar probes will be going on all the time. We're working on our Man in Space program.
Thank you, Mr. Sutton. Now, if you're all ready to head for the moon, just stand by.
Before man sets foot on our closest neighbor in space, there will be many lunar probes to test the character of the moon. Our first step is to fire a probe ahead of the moon. Caught by the moon's gravity, it makes a reverse orbit and comes looping back. In this probe vehicle, there's a television camera to give us our first view of the far side of the moon. Next, we may impact the moon with flares for the purpose of determining surface conditions. Then we'll orbit our neighbor in space with a ship carrying instruments to map the moon and give us other scientific information. Finally, we'll prepare the way by making a soft landing on the moon with an unmanned vehicle. The instruments it carries will radio back the temperature and various other conditions it will encounter. Of course, the natural climax to all these probing flights is to land a man on the moon. And that means projecting a human being on a trip of over 200,000 miles across the sea of space. As a stepping stone to the moon and beyond, manned satellites will be used. Assembled in space, the various parts of the satellite will be delivered into orbit by space freighters. Workers taken to the location by a shuttle plane will complete the job. Due to the weightless condition that exists, men will easily be able to handle equipment which they couldn't even move on the ground. The operating crew will be boosted to the orbiting satellite, and with the aid of a precise automatic navigation system, will be put into the right place with the right speed at the right time. Then the passenger carrier will overtake the satellite and transfer the crew. Periodically, the operating crew will be relieved and fresh crews transferred into the satellite. With the transfer completed, the shuttlecraft and its pilot glide back to Earth. The satellite itself will be in perpetual motion and will stay in its orbit forever, unless it is deliberately brought down. As it moves through space, the satellite might be used as a training station for personnel and to extend or increase military reconnaissance. And with men capable of making more selective observations than were previously possible, additional weather and map-making information could be collected and evaluated. Scientifically, it will serve as a telescope viewing platform, free from the heavy curtain of atmosphere that obscures the planets and stars from astronomers on Earth. Finally, a manned spaceship assembled at the satellite will leave for the moon. Arriving at the moon, the manned spaceship may go into orbit or may approach the planet directly. If the direct approach is made, retro rockets will slow it down as it closes in on the target. There will be many trips to the moon, probably serving as practice for other missions farther on, and for observation of our galaxy. The moon will be only the beginning of a tremendous new age of exploration. Beyond the moon and out to the fringe of infinity shine celestial beachheads beyond counting. And all the while we're reaching for the moon, other unmanned probes will be scouting the interplanetary skies. These snoopers, possibly using ion motors powered with vaporized metallic fuel, will ultimately head for Mars. Their ion motors supply only a small thrust, but in the airlessness of space, a little push can send the snooper rocketing along at thousands of miles an hour. As it is drawn into orbit by the gravity of Mars, the snooper's television cameras and other instruments will send back reports on this planet about which man has so many questions. Are there ruins of long-dead cities on Mars? What are the lines we call canals? Today, nobody knows, but one day the answer will be known around the world. This may be a home scene sometime in the 1980s, perhaps even sooner. From a manned spaceship heading for Mars will come one of the most exciting on-the-spot telecasts in history.
This is Commander Wilson reporting to Earth from Operation Mars. This is the 260th day of our voyage. We will soon begin orbiting as soon as we come within the pull of the gravity of Mars. All members.
While planetary exploration will become a reality, it's not as easy as some people would have us believe. We're dealing with tremendous distances. Earth is 93 million miles from the sun. Mars is nearly 49 million miles beyond us. Saturn is 480 million miles from the sun. And the planets stretch out clear to Pluto, nearly 3,700 million miles away. The nearest star in our galaxy is Alpha Centauri, which is 3,000 times as far away as Pluto. And our galaxy is only one of the many island universes that extend beyond our conception. Besides the problems of distances, we still have much to learn about cosmic rays, radiation, meteorites, and the effects of weightlessness. There's more to be known of the different kinds of power. But we're learning more every day with every test. And with every missile probing the wilderness of space. There's only one question for which we have the final and absolute answer. Will man conquer space? And the answer is yes.
And why does man reach out to learn the secrets of space? Did Columbus know? Or Leif the Lucky? Or Magellan? Cortez? Sir Francis Drake? Could any of them put into words the call of unknown seas, the strange fascination of distant horizons? West of these, out to seas colder than the Hebrides I must go, where the fleet of stars is anchored, and the young star captains glow. Above and beyond us arcs the sea of space, and the enchantment of the far unknown stirs the spirit of the explorer. Restless, curious, man will conquer space because he wants to know what lies over the hill. What lies beyond the barriers of Earth? His very existence is a challenge, and the end of that challenge is the farthest sweep of the imaginative mind of man.
Here at Edwards Air Force Base, September 17, 1959 is a historic date. Early on this Thursday morning, the B-52 carrier takes the X-15 out for its maiden powered flight.
Hydraulic temperature, Scott? -2, and holding since we passed the tower.
Test pilot Scott Crossfield is buckled in and ready for a ride to 40,000 feet, where he'll be cut loose for the first demonstration of this plane's abilities and performance. Flying chase will be Al White, North American's alternate, Joe Walker, NASA's chief test pilot, and the Air Force project pilot, Major Bob White. All vital observers today. They'll be at the controls of the X-15 in the near future. Ground crews climb in a variety of vehicles and stream out to wait for landing at the edge of the lake bed. Many eyes are on the dart-shaped plane this morning, but among the most important observers are the engineers at NASA. Using the ears of radio and the eyes of radar, they'll keep a close watch on the flight. FM signals transmitted will indicate the condition of each vital operating system. Each movement will be carefully plotted, carefully watched.
Edwards
003, Edwards, cleared for takeoff.
Winds 220 degrees at 12 knots.
Prime responsibility for getting the X-15 to drop altitude rests on the aircraft commander, Captain Charles Bach, and the co-pilot, Captain Allaby.
Any tower, 003, rolling now.
As the bomber climbs out, the litany of checkout drones on, item after item. Gauge, switch, and control are checked and rechecked. In the dim interior of the 52, Bill Berkowitz, launch monitor, has a close-up television view of system operation. The group has been this route before. 2 tries, 2 misses. The first try never left the ground. The second came agonizingly close, just 3 minutes from a drop, when a frozen valve canceled the effort. Delays are difficult to accept, but each time the system at fault was improved and a problem eliminated.
APU is coming on now. First. Right. Number 2 on now. Real slow to pick up hydraulic pressure.
Blake, how about it? It's a little slow, but it's up to speed now.
It grabbed off in about 5 seconds, and it did go over 3,600. No flat, 510 on the tank. 3 minutes to drop. Flying to jettison. Fuel jettisoning. Full jettisoning. Okay, good check. Prime's coming on now. 6 call prime, watch out there, I can't see it. Yeah, I got, you got a blossom on the bottom one? Yeah, they're both looking good. 30 seconds, give me ready to launch light. Put a launch light on. Launch light on, master on.
How about it, Blake? Think we're okay?
Ready?
All right, by me, let's go. Okay, Scott, let's give it a try.
Okay, Scott, you ready? I'm ready when you are, buddy. Okay, here we go with the countdown. 3, 2, 1, release. Got 8 of them going. Roger. Heading uphill at 33,000 feet. Roger. Looks good across the board. And I'm on number 1 and climbing to 35. Roger. Direction looks good, Scotty. Right on, you look real good. Okay, fine. One up on 50. Level. Right.
The course for this flight is a giant rectangle around the lake, climbing to the north, then making a left turn to a westerly heading, and leveling off at 52,000 feet.
Take a little speed, I'm gonna ease off. Right. Left turn. Roger. I'm beginning to come around the final part of the turn. I dropped back in Mach number.
The record showed Mach 2.1, over twice the speed of sound, 1,385 miles an hour.
Run out. Roger.
On the first try, man and plane went 1/3 the way to the goal of 6 times the speed of sound. As the X-15 slows to subsonic speeds, the chase planes catch up and the glide portion of the flight begins. Now on a southerly heading, Crossfield begins his long glide to landing from 46,000 feet. Time in the air is precious, and the checkout continues all the way down.
Roll probe. Steady side slip. Very powerful rudder on this little lady. Got ventral. Okay, buddy, just a second. 8,000. I want to drop it on the track. Here comes ventral now. You ready? One, parachute. No, fouled up. Roger. You're fouled up? No, the parachute. Well, it's open. It's letting it down. How nice. 245. It's pretty good crosswind, isn't it? Little bit, yeah. 240. Still 240.
Maiden flight, a success. Today, flight research took another significant step forward here at Rogers Dry Lake. This lake bed has witnessed many significant events in the history of aviation. Born this day was a new tool for flight research. Using a new machine to probe into the unknown calls for caution, and weeks later the second flight showed that the performance could be repeated and excelled. Digesting the knowledge from these first tries, the program became more ambitious, and another step up the ladder was planned, one that would extend the operating area. Countdown for powered flight begins at midnight. The previous week has seen many test hurdles, each one met and overcome, each one establishing with greater authority the right of the X-15 to be in this fueling area. All the control points have been passed this far, and now the touchy, toxic, volatile propellants are added one by one. As tanks are gradually filled, crew members take long last looks into the vitals, then close the doors. Dawn finds the service cots being pulled away, with the 2 aircraft again standing ready. Even the most carefully controlled experiment has its element of risk, and the sober faces of every member of the team reflect their concern. Each research flight has fresh new goals. Each one is a cautious step forward into unexplored areas. The intention of this flight is to make a straight climb to 80,000 feet, hitting Mach 2 at the peak. The now routine checks of plane and engine pass uneventfully, and just past 9 in the morning, the third voyage of the X-15 begins.
I got fire, Scott. Like shut down. Please shut down. Shut down. Collected ships. Land on Roosevelt.
In a split second, the plan of exploration is abruptly changed to one of survival as the pilot fields out the plane for damage and heads for Rosamond, an emergency landing area. Never has the pilot been more vital. Now it's his responsibility to get the plane on the ground safely if he can.
Yes, Scott. Yes, that's all anytime. That's what's going on now, watch. It's off, it's off. Love it.
Trouble came in pairs on this day. The engine failure was complicated by a structural break, and both were at this time unexplained. The plane was on the ground, the pilot safe, but there were new problems. Investigators found that the rocket engine had suffered an ignition failure, leaving a chamber loaded with explosives. When this mixture finally ignited, the chamber ruptured. This explosion triggered another series of events leading to additional damage. Under normal conditions, the tanks are almost emptied, but jettison in a nose-down emergency glide leaves more propellants, more weight in the fuselage. Because of this increased weight, the nose of the plane had to be higher than usual during landing. Although the touchdown was smooth, the nose-up angle was beyond the design limits, and the break occurred when the nose wheel slammed to the ground. A day and a half after the accident saw the airframe in its original jigs at the factory. The damage that seemed crippling was quickly repaired, and the broken halves rejoined. This whole project is one set to gain knowledge, and even from failures, lessons are learned. The fuselage was strengthened and landing gear was redesigned to absorb more shock. The rocket engines were modified to increase reliability. 5 weeks after the unsuccessful try, the plane, now whole and improved, began its trek back to Edwards Air Force Base. Weeks have slipped by since the accident, but the time has been traded for knowledge. More is known now. Certain hazards have been ruled out. The machine is better, more able. This is the #1 plane of the series, modified, improved, and set to show its capabilities. It hangs frosted, smoking, ready. Pouring on the rocket power, the X-15 streaks to a new high of Mach 2.5, 1,660 miles an hour at 67,000 feet. January saw the #1 airplane make its final qualifying flight. Delivery to the Air Force and NASA started a new crew on acceptance check and pre-flight readying. Joe Walker, Chief Research Pilot of the National Aeronautics and Space Administration, was the first to show that the X-15 is not a one-man airplane. At this time, 2 X-15s were flight ready. Number 1 was involved in the Air Force NASA program to take the airplane with its present engines and push it to the limit of its abilities. And Joe Walker's first flight denotes the start of this research phase. The number 2 plane was still being flown by North American for investigation of stability, control, flying qualities.
Okay, that's nice, Joe. Turn a little to the right now. I would say that's okay. Okay, we got all 8 going now. Roger, everything looks good. Okay, I'll need a second on how far out I get now. Okay.
The drop was standard, the flight routine, the landing uneventful. 2 weeks later, another new face appeared. Major Bob White climbed the ladder to the cockpit to try his hand at rocket plane flying. An hour and a half later, the X-15 Pilots Club had another new member. The Air Force's project pilot had made his initial run and now was ready to start some serious research flying. The spring of the year saw a flurry of activity with 2 X-15s flying and North American racking up 9 drops with the number 2 airplane. The Air Force and NASA alternated pilots on a separate series of 9 research expeditions, flights that kept inching up on the world speed and altitude records. Both company and governmental pilots kept investigating the flight abilities of the planes in different quarters, feeling out the new machines, steadily pushing the operating area out farther, gaining confidence. All flying during this period was done with the XLR-11, the small engine package. Its thrust of 16,000 pounds was adequate for early investigations, but everyone was waiting for the big engine. The XLR-99, a brute that would blast out nearly 60,000 pounds of thrust to drive the plane to peak speeds and altitudes. This engine is installed in the 3rd and last plane of the series, which has always been slated to be the test bed for this new power plant. And Crossfield uses his time in between flights to ring out the installation. Preliminaries are out of the way, and this run will be one of the final before flight. This long-awaited engine can be throttled, having an idle output of 30,000 pounds, but able to be regulated between idle and 60,000 pounds of thrust. Today's runs are the climax of a long series of tests proving the installation. After this start, they're ready for flight.
Valve malfunction. Throttle off. Reset.
In a split second, years of planning, months of test and grinding work went up in smoke. There was only one real observer, one eyewitness, the pilot, Scott Crossfield. Scott, what was your immediate reaction?
Well, it was the biggest bang that I'd ever heard. Fortunately for me and the airplane, the explosion blew the forward section, the tanks, and the cockpit out of the blaze, or out of the major part of the blaze. And the firemen were right on their toes, and they moved in to blanket the tanks and the fire area with foam. The first reaction we had was that the engine had blown up, but like many first impressions, this was wrong. As soon as the parts cooled down, a disenchanted group of engineers moved in, and as you might imagine, things were pretty well scattered about. We also took a close look at the film that you've just seen, and here are a couple of frames that gave us our first clue. Just before the blow-up, a cloud of vapor appeared ahead of the engine. So the search was concentrated on this area. Following up this lead, we found that the hydrogen peroxide tank had been rammed, smashed open. But with what? Lining up with the tank is the center structure of the ammonia tank, and its shape matched the impacted area of the hydrogen peroxide sphere. But how could this part fail? Likely through overpressure. Now, a check of the instrumentation showed tank pressures far over normal. Again, the question, why? The pressure regulator was recovered and checked. It was determined that freezing caused by the very low temperature pressurizing gas had caused the regulator to stick full open. But there's a safety, a valve to relieve overpressure. This valve and the entire release system was also checked. Here it was determined that a flow-sensitive relief valve combined with a vapor disposal equipment had created enough back pressure to fail the tank. So, a frozen regulator, a Foley relief valve, and a high back pressure relief system had gotten together and we had wrecked an airplane. The entire pressurizing and release systems were analyzed, redesigned, tested, and retested. We ran the combination time after time, deliberately creating the most severe failures possible. Weeks passed before we and everyone else were convinced that the problem was licked. As a measure of how the confidence was restored, here is what happened on the 4th of August.
On this historic date, Joe Walker let out a yip of joy. He had just pushed the modified small-engine airplane to a new speed record, then made his report to the public.
Joe, how does it feel to be the fastest living human? I don't know if I feel much different than I did yesterday, except that the waiting for the flight is over, finally.
60-165.
Call it back area, Joe.
Roger.
Gyro lifting.
Deployed. Please, over. Go. Burn out. +3+.
You made it. At what point did you reach your maximum speed? If you noticed the vapor trail from the engine, at the instant it cut off, that was the point at which I reached the maximum speed.
Now, what was your altitude then?
Around 66,000.
How long were you going that 2,150 miles?
Just one instant.
Then, on the 12th of August, just 8 days later, Major Bob White was up before the cameras after his 136,500-foot record-breaking altitude flight.
The flight today offered, I would say, no problems and nothing that could be considered a limitation as far as man's ability to fly an aircraft.
We'll pull up. Right. Right on the track. Your angle looks good, Bob. You're going up. Pass 9.
Once I pitched up and reached the highest climb angle, I was very definitely impressed that I was going, well, almost straight up. Of course, it wasn't straight up, but it appears to be that way from the cockpit.
That's coming up on 10 now. Okay. Angle's very good. Going through 11 now. Burn out. Burn out now at coming 12 now. Got 12.6 and 13.
Very sensitive.
That's still good.
Fantastic up here.
What you see at this altitude impressed me as being the most dramatic point of flying at over 130,000 feet. The very dark blue sky and the lighter band that was immediately surrounding the Earth, and then, of course, the many, many miles off in the distance that you're able to see. Looking to the future, I would say that we hope very much, and I would particularly like to continue on in work that would take us to higher altitudes with manned aircraft.
Now the full potential of the airplane with the small engines had been fully investigated. While the number 2 airplane was being fitted with the big engine, number 1 began a series of training flights. The full crew was now given a chance to try its hand at piloting the research plane. Commander Peterson, the Navy's representative, was the 4th man to ride the X-15. He made 2 flights in early fall. Then Jack McKay, NASA research pilot, took his first ride at the end of October. Captain Rushworth, the Air Force backup pilot, was next to show his skill at rocket plane flying. NASA pilot Neil Armstrong's last 2 flights closed the year. Training flights filled the gap while the number 2 was being given a complete checkout with the large engine. Since that ill-fated day in June when the explosion ripped the number 3 ship in half, maximum effort has been exerted toward getting another engine and installing it in Ship 2. Months of work, weeks of painstaking trials, round-the-clock days of final pre-flight were at last put to the test on the morning of November the 15th. This is the X-15 in its final stage of development. This run, if successful, will mark the beginning of a whole new era of flight research.
Camera. This is awesome. It's okay, down here, Scott. Okay to go? Right. Roger. 25. Pump idle. Idle cooling, got down. Got it. Launch. Turning up to the right, Scotty. The launch tank pressure is going up to 60. And I'm going uphill. I'm reading 320. Launch tank is holding at about 55. About 1-2, dive brakes coming open. How's it look, Al? Looked real good, Scotty. You made about a 10-degree turn to the right when you came off.
With the new engine loafing at idle, the plane could go to 4 times the speed of sound. So the speed brakes are open to stay close to Mach 2.
It's good, Scott. A little to the right, of course. You're okay.
Firing ready, Rob. Scott, could you tell us in your own words how the flight went and what you thought of it? Very well, and the engine and its power is impressive. What was your maximum altitude and speed? Did you have a chance to check that yourself? Yeah, I got about 80,000 feet and a Mach number approaching 3.
Scott, your radio talk sounded a bit hesitant this morning before takeoff. What was that about?
Oh, no, I think you misinterpreted that. Of course, we've been doing the best we can to get this flight off for 5 years. There's any hesitancy there.
Scott, having observed the minimum thrust performance of the engine, do you think that the airplane now will be able to live up to its design promises of altitude and speed, or will exceed it, or how do you feel?
Yeah, really without question. I got a little faster today than we'd planned, and we have in our previous flights, in my flights, gotten faster than we'd planned, because for once in history we've overestimated the drag on the airplane. I think it'll exceed its original expectations.
Just 7 days later, the second flight was launched, and on the 6th of December, the third. Both showed the engine to have all the abilities claimed of it. These 2 eminently successful flights closed the year. But the story of the X-15 stands not in the past, but in the future, when every flight is a record breaker, when every trip away from the B-52 is an unparalleled research mission. Human hands will be learning a new skill, to thrust deep into unexplored areas, capture vital information, then settle to a safe return from that twilight land standing between Earth and space.
Okay, your position looks good, Joe. Let's go Delta Psi on.
Haven't gotten to 1 minute warning yet.
Your position is good, Joe.
Pump idle. Good pump. Good igniter. Ready to launch now. Good light. Okay.
This is the X-15 research aircraft, designed to investigate the problems of manned flight in a near-space environment. Altitudes up to 50 miles, speeds up to Mach 6. High-speed aerodynamics, aerodynamic heating, structural design, aircraft stability, and control in space and re-entry. This was the kind of information it was to provide, and provided it did. Here's the story. Before the X-15, the question had been, what is to be man's role in space travel? Can he pilot an aircraft out of the Earth's atmosphere, fly it in space, then re-enter the atmosphere and bring it back to a safe landing on Earth? There were many unknowns to be discovered, many problems to be overcome before the answer would be known. That today's test flight is almost routine is a tribute to the comprehensive program that has moved step by step to prove that man can pilot an aircraft into space and return.
Give us a 20,000-foot check, Joe.
Coming up on 20,000 now.
Okay, I know you've done it, but check your flaps and circuit breakers.
Roger. Done.
Ready to go pressurized?
Pressurized.
You're in good shape. Real good flight, Joe. This is your happy controller going off the air.
There have been many men who have helped make the X-15 project a success. One of them is aircraft research engineer Hartley Soule, who was originally in charge of designing and building the X-15 aircraft.
Of course, I'm retired now. And the X-15, she's not the queen of the hangar anymore, although she's still hard at work. But I remember years ago, you know, it was long before Sputnik that we decided to build the X-15. This airplane, the first hypersonic aircraft, was going to be our first manned space probe. This was a logical step in the research aircraft program that had begun even before the end of World War II.
From the beginning, the research aircraft program was a cooperative affair. The National Advisory Committee for Aeronautics, predecessor to NASA, the aircraft industry, the Air Force, the Navy, working together. Their first effort was directed at breaking the sound barrier. And the aircraft that would do it was the X-1, designed to acquire flight data at the speed of sound. On October 14th, 1947, with Air Force Captain Charles E. Yeager at the controls, the X-1 made the world's first supersonic flight. Other research aircraft soon followed the X-1. The Douglas D-558 Phase 1 to investigate flight with a straight wing at high subsonic speeds. The Northrop X-4 designed to fly without a tail. The Douglas D-558 Phase 2 to study flight characteristics of swept-wing aircraft at transonic and supersonic speeds. The Bell X-5 designed with variable sweep. And the Douglas X-3 to investigate thin straight wings at speeds beyond Mach 1. The Bell X-1A, with its increased performance, first of a series of follow-on aircraft to the original X-1. The X-2, another Bell airplane designed to explore aircraft behavior at altitudes above 100,000 feet and Mach 3 speeds. The X-1E and X-1B, both later follow-ons to the X-1. Step by step, these different aircraft helped nibble away at the unknown, until by 1956, the frontiers of manned flight had been advanced from speeds of 500 miles an hour to Mach 3, and from altitudes of only 40,000 to more than 100,000 feet.
Speed, altitude, sure we kept going higher and faster than we'd ever been before. Only because that's where new information, where the unknown has always been found in flight, above and beyond the limits you've already reached.
As early as 1952, the X-15 aircraft was being conceived by the people at NACA. At the Langley Center in Virginia, they began investigating the unknowns associated with flight to the thinnest edges of the Earth's atmosphere. One unknown concerned aerodynamic heating. The X-15 would be the first aircraft to push from supersonic to hypersonic speeds, where the flow of air would heat the leading edges of the plane to 1,300 degrees Fahrenheit. Experiment after experiment was run to see if this extreme temperature would weaken or melt basic materials. The data resulting from tests run well beyond temperatures expected for the X-15 proved that there were materials that would withstand this kind of heat. Another problem, after rocket engines shut down, the X-15 would be thrust into a ballistic arc in air so thin that normal aerodynamic control would be impossible. How then could the pilot control the aircraft? The answer? Reaction controls that would allow him to correct roll movement and position the aircraft properly for re-entry through the atmosphere. But the designers knew the problems of control would never be fully solved until an X-15 aircraft was actually built.
We knew the X-15 would look something like this. We knew that it would be a manned aircraft that would fly more than 4,000 miles an hour and as high as 250,000 feet. We knew that, like the X-1, the X-15 would be air-launched and propelled in its flight by a rocket motor, the most powerful engine ever installed in an airplane. Of course, we didn't know what kind of a rocket motor that would prove to be.
There'd never been anything like it. Designed for a manned system, the 50,000 pounds of thrust in its single chamber had to be controllable at the pilot's discretion. He had to be able to throttle this engine in flight.
This is Harry Cook, program manager for the X-15 rocket engine.
The LR-99 rocket engine was designed and built for the X-15 by the Reaction Motors Division of the Thiokol Chemical Corporation. We had some experience in this field. Reaction Motors had built power plants for all of the X-1s and for the D-558 Phase 2 aircraft. But those rocket engines we had made for earlier research planes were primitive forerunners of the engine we built for the X-15.
57,000 pounds of thrust with a throttle attached. No engine like this had ever existed before, but Thiokol built one for the X-15. Now, What kind of airframe could be designed to carry such an engine?
The X-15 was designed and built to take the stresses encountered at hypersonic speeds, to go to extreme high altitude and to beat the heat, survive the extreme high temperatures that build up on the wing, fuselage, and tail during the re-entry to the Earth's atmosphere. The engineering research contribution we made at North American Aviation to the X-15 project was to take NASA's proposal to build this aircraft and to find out how they could be met.
Harrison Storms. He was in charge of the X-15 program at North American Aviation.
For example, they proposed to use a new nickel alloy metal for the protective sheath or skin on all three of the airframes of the X-15. We had to find out how it could be used.
Inconel X was the name of the new nickel alloy. It was developed to withstand the searing temperatures at hypersonic speeds, temperatures of 1200 degrees Fahrenheit or more. But to use Inconel X, it had to be cross-welded, and no one had been able to do it before. A major milestone was passed when North American discovered how it could be done. North American also originated the idea of fairings along each side of the X-15 fuselage to house control cables and hydraulic lines. This left the entire fuselage volume for power plant plumbing, as well as fuel and propellant tanks. Another invaluable North American contribution was the X-15 flight simulator, permitting pilots and ground controllers to plan and practice flights without ever leaving the ground. From an exact replica of the X-15 cockpit, the pilot could actuate hydraulic and control systems identical to those on the aircraft itself. All this was tied into an analog computer that could program actual X-15 missions and simulate every conceivable in-flight problem the pilot might expect to face. Practice in the flight simulator was just one phase of pre-flight preparation. Another took place in the centrifuge at the Navy's Air Development Test Center at Johnsville, Pennsylvania. There, pilots learned how to take the heavy G forces they would meet when they flew the X-15 up into space and back down again. Hours of training here, added to hours in the simulator, extended the pre-flight pilot training period into weeks and even months. Then came the dramatic moment. The X-15 and its B-52 launch aircraft were ready. North American test pilot Scott Crossfield was ready. Step by step, the X-15 research project had moved to this important event. Now, the first of 3 X-15s was about to begin a series of test flights. The schedule called for an orderly progression of tests. In the first flights, the X-15 would remain attached to the B-52. Then a glide flight would be tried. Only then would powered flight be attempted. This careful program of flight tests, flown by pilot Scott Crossfield, proved the X-15 would do just what its designers hoped she would.
From March 10th, 1959 until late in 1960, when we delivered the 3rd aircraft to the Air Force, I made 14 captive flights, 1 glide flight, and 10 powered flights. It was all pretty much routine. We, North American that is, went up there to check out the aircraft, to check out the systems, to see how she handled and whether or not she'd meet the specs before we turned her over to the Air Force. But you'll have to go up to NASA's Flight Research Center at Edwards to find out how the actual test programs worked.
Edwards Air Force Base in the Mojave Desert in California. This is where the X-15 story comes together. For here is where test flights of all high-speed research aircraft since the X-1 have taken place. Like all the programs conducted here, the X-15 Flight Research Project had a simple basis. A series of progressive steps to higher speeds and to higher altitudes. But each step, each flight itself, had a more immediate purpose than simply to gain more speed or altitude. And each flight was carefully planned to make the most effective use of this aircraft as a research vehicle or tool. Paul Bickel, director of NASA's Flight Research Center.
Each flight provided new information or confirmed one tunnel or theoretical data on the characteristics of an airplane performing in a very advanced flight regime. Each flight grew out of one that had already taken place and led to another still to come. But of course, the X-15 flight program really began in the simulator months before the first airplane was delivered to us.
Joe Walker, Chief NASA Edwards research pilot, physicist, and pilot of a long list of research aircraft.
Practice or planning in the simulator is the beginning of every flight that's ever been made in the X-15. All pilots assigned to the project first become familiar with the handling characteristics and timing of the X-15 on any given mission in the flight simulator. It's been good insurance for all of us.
One of the X-15 pilots who has spent many hours in the flight simulator is NASA's Milton Thompson. Here, Thompson flies a practice mission under normal procedure, with pilot engineer John McKay working as his flight planner. In a nearby room where the analog computer is housed, the activity in the cockpit can be monitored on closed-circuit TV. The pilot's control movements and the airplane's simulated response are checked on a plotter by the flight planner, who will monitor the actual flight from the NASA Edwards Control Center on the ground. The pilot's inputs may also be monitored and recorded by other instruments. Variations from the planned mission are then simulated, so the pilot will learn to recognize their effects on the aircraft. For example, he may get a problem involving changes in stability. These changes are fed by the computer to his cockpit instruments. The pilot reads the changes and makes control inputs to bring the aircraft back to normal. His response is monitored and evaluated. The pilot also goes through what is called trouble school, where failure of one or more of the X-15's major systems is simulated. Again, his reaction is monitored. Each pilot gets further practice by making a number of flights in a modified F-104 aircraft. He flies over his upcoming X-15 flight course to establish geographic checkpoints and key altitudes in the landing pattern. All flights are made over the high range, a network of ground tracking stations stretching from Wendover, Utah, 485 miles south to Edwards in California. The range consists of a master station at Edwards and radar stations at Ely, Nevada, and at Beatty. The flight corridor is 50 miles wide, and it contains a number of dry lake beds where emergency landings can be made. Two kinds of powered flights are made over the high range. One, a ballistic type, high-altitude run up to and even above 250,000 feet. And two, a high-speed run made at a lower altitude, usually 60 to 70,000 feet. During his practice flights in the F-104, the pilot must also familiarize himself with the timing and positioning for an X-15 landing at both primary and alternate landing sites. And he makes practice landings, using predetermined settings that can simulate the low lift-drag ratio of the X-15. Nothing is left to chance, in the air or on the ground.
These precautions paid off during the following flight, when the pilot realized he could only get 30% power, and that consequently he would have to make an emergency landing at Mud Lake.
Ready to launch. 5, 4, 3, 2, 1.
That's a good light, that's a good light.
Hello, on front, give us the chamber reading.
Got 12 degrees.
Okay.
Chamber pressure.
Tank pressure's a 50.
Push your throttle up and give us chamber pressure.
We don't have to take pressure about 200.
Roger, you got full throttle?
Confirm.
You're running at 30%.
30%? How are we doing, Bob?
Roger, you're going by Mud Lake. It looks like a landing at Mud Lake.
Roger. Looks from the smoke down there like there's a very tiny bit of wind from perhaps south and a little bit east, so it's not...
Wrecked though it seemed to be, both the aircraft and the pilot survived to continue with the program. This was one of only 3 major accidents, all non-fatal, that have occurred in more than 120 flights with the X-15, a remarkable record of reliability. In February 1964, the plane that crashed on Mud Lake only a few months before came rolling out of the North American plant with a new designation, the X-15A2. This modified version was rebuilt for flight to Mach 8, 8 times the speed of sound, where the airflow temperature rises to 2,400 degrees Fahrenheit. The new X-15 had a new heat-resistant protective coating, a new inertial guidance system, a longer fuselage, external tanks to carry more fuel for longer flights, and lengthened landing gear. All the while this new X-15 was being built, tests were continuing with the other 2 aircraft, and they continue today. For every flight, the procedure is essentially the same. Every phase carefully planned, every second of actual flight time mapped out in advance. That way, every man involved knows exactly what his job will be from the beginning to the end of the flight. Hours of preparation, weeks of planning, months of study, whole years of research. All this goes with the X-15 each time she leaves the hangar for another flight. For after all, no matter how many flights have been made before, each new test will probe a little deeper into the unknown. She is a research tool, this sleek black aircraft, carrying a host of instruments, gauges, and recorders to explore the unknown. And every second of her time in flight must be carefully charted. That's why at the Ely High Range Station, at Beatty, at Edwards, sensitive antenna watch and listen to each flight. That's why the pilot's heartbeat never really leaves the ground. And that's why in each control room on the ground, the plotting board is carefully watched for any unplanned deviation, for any unlooked for change in the pilot's reactions or in the behavior of the aircraft. Position and velocity computers, telemetry receivers and monitors, data receiving and recording equipment, communications receivers and transmitters, they all go into action at the beginning of every flight. In NASA 1, the project men stand by, alert for any possible trouble in the flight, while flight surgeons prepare to watch the pilot's physiological response, his pulse, his body temperature, heart action, respiration rate. All of this will be telemetered to the ground. Then, as always, when time for takeoff draws near, attention focuses on the man chosen to fly the mission. Because of this, the X-15 pilot becomes, in effect, the symbol for the entire research team. The one man who represents all the others who have worked so long and so hard to make the project a success. And it is a proud record of accomplishment they've achieved. They have designed and built an aircraft that could be piloted into space and flown back safely to a controlled landing on Earth. They have accumulated important data on aerodynamic heating at hypersonic speeds. They've learned about stability and control of aircraft during flight in near space and re-entry to the Earth's atmosphere. And perhaps most important of all, they have dramatized the potential of piloted high-performance aircraft in a space environment at a time when much of the world's gaze was turned toward orbital flight. The X-15 research project has long since achieved its original goals. The aircraft has been flown successfully more than 120 times, and although setting new records wasn't its purpose, it has set a few along the way. Altitude, 67 miles. Speed, Mach 6, 4,104 miles an hour, the highest and fastest a winged aircraft has ever flown. Today, the X-15 moves on to further accomplishment. But now the Thoroughbred has become a workhorse, carrying a heavy payload of instruments, undertaking studies of the near-space environment possible before only with unmanned satellite and rocket-borne probes. There are many people who should share the credit for the continuing success of the X-15 research project. But perhaps they will understand if we seem to focus on those who have actually flown the many research aircraft since the X-1. By saluting these courageous men, we also pay homage to all the others who have helped us move step by step, deeper and deeper, into the unknown outskirts of space.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunkworks' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortress, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. for more amazing aerial footage. And to join us in this incredible journey, check out the DroneScapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.